In this video, we're going to look at a question, on hollow sphere of radius 2 cm carrying a charge of plus 4.8 times 10 raised to the minus 12 Coulomb. We are asked to calculate the capacitance of the sphere and then the potential difference on its surface. Now, to attempt this question, first of all, let's bring out the parameters from the question. This is 2 cm, because the 2 cm is the same as 2 times 10 raised to the minus 2 meters, divided 2 by what? 100. Then, the charge that the sphere carries was given to us to be 4.8 times 10 raised to the minus 12 Coulomb. We have to calculate the capacitance of the capacitor, we don't know. Now, for a charged sphere with radius, we already derived the equation that the capacitance of such sphere is giving us 4 pi E naught times R. Is that okay? E naught times R. The E naught is permittivity of what? Free space, which is 8.85 times 10 raised to the minus 12 farad per meter. So we can substitute there directly, and then capacitance will give us 4 times pi, then times pi there 3.142 or 22/7. Then the permittivity of free space is 8.85 times 10 raised to the minus 12 times the radius of the sphere, which is 2 times 10 raised to the minus 2 meters. Now if you solve this out, let's see what we're going to get. 4 times 3.142, we're going to multiply by 8.85, then multiply by 2. From here it's giving me 222.45, then times 10 raised to the power. We can add the powers of 10 here. That's going to give us minus 14. Now if you work in this by moving points, this is in farad already, but we can still move our point 1, 2, so have 2.22, then times 10 raised to the power. We'll move the point 2 times to the left, so we're going to add 2 to this minus 14, which will give us minus what? 12 farad. Does that make sense? This is the same as 2.22 picofarad. Remember, 10 raised to the minus 12 is pico. And we're going to leave a result in farad. But please take note, suppose this sphere is placed in a given medium, and then the dielectric constant value of that medium is given. What will this formula become? We won't just use E naught, we won't just use permittivity of free space. We're going to use the permittivity of the medium. Where in that case, we know that our permittivity of the medium will now be the dielectric constant relative permittivity times the permittivity of free space. We're going to substitute it for this permittivity of free space there. So take a look. Now let's look at the second part of the question. We have to calculate the potential difference on its surface. We don't know. There's electrical potential, but you know that the relationship between electrical potential and capacitance of the capacitor to charge. We have it as, so we're going to say recall, we have it as V is equal to 1/4 pi A naught, and this is a constant, so we're going to multiply by what? The charge divided by the distance, That's the radius of the sphere. Of course, this equation you know is still the same as writing V is equal to Q over what? C. Does that make sense? So either of them you use, you still get the same result. If you're using this, 1/4 pi A naught is 9 times 10 raised to the power what? 9. Take note of that. Then multiply by the charge divided by the radius. So I'm going to use this formula, They will still give you the same thing. So you can work it out using this. But take note, 1/4 pi A naught is a constant, 9 times 10 raised to the power what? 9. Let's substitute here and see the charge on the sphere is given to be 4.8 times 10 raised to the power minus 12 Coulomb, and then divided by the capacitance, which we already calculated to be 2.22 times 10 raised to the power what? Minus 12 farad. Of course, the potential difference, or electrical potential in this case, what's going to happen here, this and this will go off. We're going to have 4.8 divided by 2.22. So from my end here, it's giving me 2.16 volts, alright? So this is the potential difference on the surface of the sphere, whereas this is the capacitance of the sphere. In this video, we look at a square parallel plate capacitor of size 25 cm and separation of 1.5 mm maintained at a potential difference of 300 volts. We are required to calculate the capacitance of the system and the charge on its plate. And then again, suppose the separation is filled with mica dielectric of relative permittivity of 7, that is dielectric constant of 7. Calculate its new capacitance and charge. Now we're given the permittivity of free space, 8.854 times 10 raised to the minus 12 farad per meter. And in solving this problem, you would recall that as a strategy, first of all, we define the parameters, the data that we know from the question. Of course, we've defined that the length of the square parallel plate is given us 25 centimeter, which is 0.25 meters by dividing 25 by 100, so as to express it in meter, SI unit. Now the distance of separation between the two plates is 1.5 millimeter. You have to convert to meters by dividing this 1.5 by what? 1000. It's the same as multiplying 1.5 by 10 raised to the power minus 3 expressed in meters. Now the potential difference is given to us to be 300 volts. So to get our capacitance under this condition, in the first case, of course, you know there is no dielectric medium mentioned in the first case of the question, and so it means we're going to take it as what? Vacuum. So we are looking for capacitance, we don't know. We are also to get a charge, in that case we don't know. First of all, let's seek for the capacitance. You will recall that capacitance of a capacitor with permittivity of free space is giving us C equal to, that's going to be E naught times A divided by what? The distance of separation. That's permittivity of free space times the area divided by what? The distance of separation between the plate. Now the area will have to be calculated from taking into account that the plate is what? A square plate. Is that okay? And so for a square, we now want to talk about the area of the square. Very important. Because this problem, it could have been that the parallel plate is rectangular in nature, and so you will seek for the area of a rectangle, which is length times width. In that case, the width of the rectangle will be given, alright? Now, this question is based on what? Square. So the shape of the plate is square-like. So the area of the square, we're going to obtain it, and you know for a square, the area is length square. That is the square of any one of its sides. So it means that this formula is going to be written as this, then area of the square is length square divided by what? The distance of separation. Does that make sense? Take note that this length square represents what? The area of the plate. So we move on, we can now substitute that this is now equal to 8.85, alright? Think 8.854, then multiply by 10 raised to the power minus 12, then multiply by square of the length, which is the area, 0.25. You're going to square it and then divide by the distance of separation, which is 1.5 times 10 raised to the power minus 3. We can now obtain our value by pressing these values in our calculator. Let's do that and see what we're going to get. That's going to be 8.854. We're going to multiply it by 0.25 times another 0.25 by the square of that value. Then I'm going to divide by 1.5. So from here, I'm getting 0.37 approximately times 10 raised to power. Now this 10 raised to minus 12 and then 10 raised to minus 3. We move this minus 3 up, it will change to plus. So minus 12 plus 3 is going to give us what? Minus 9. This can still be expressed as 3.7 times 10 raised to power. What did I do? I moved the point from here to this between 3 and 7. Because ordinarily we prefer that a non-zero number appears before a decimal point, okay? It's not like a rule, but just formal. So moving the point one time to the right means I'm going to subtract 1 from this minus 9, therefore making it what? Minus 10. So this is the capacitance in the first case of the question. We now want to get the what? The charge. Is that okay? We want to get a charge on the plates. So for the charge Q, alright, we're going to recall that Q is equal to, recall that Q is equal to CV. You know that capacitance of a capacitor is equal to charge divided by voltage. So if you cross multiply, you get a charge to be equal to capacitance times the voltage. So you can substitute, the capacitance is 3.7 times 10 raised to the minus 10 calculated already. So we're going to multiply by the voltage, and that the voltage that the plate is maintained at is 300 volts. Once again, we'll reach out for a calculator. Let's see what it's going to give to us. So I have 3.7 multiplied by 300. It's giving me 1,110 times 10 raised to the power minus 10. That's going to be in column Okay, once again, I might wish to move my point from here, go 1, 2, and 3. Okay, so that this will still be 1.11 times 10 raised to power. I move to the point 3 times to the left. So I'm going to add 3 to this minus 10, which will give me minus what? 7 Coulomb. So this becomes the charge on the plate. We're going to take a break. When we return from the short break, we'll now focus on the second part of the question, when the space between the plate was filled with a dielectric material mica with dielectric constant of 7. And now, you're welcome from the short break. We want to look at the second part of the question. Suppose the separation is filled with mica dielectric of relative permittivity 7. Calculate its new capacitance and what? Charge. In the second part of this question, we don't have a dielectric material whose dielectric constant, that is relative permittivity, is what? 7. So we have to obtain the capacitance in that case, as well as the charge on the plate in that case. Alright? So it's pretty simple. Okay? It's just for us to replace the permittivity of free space with the permittivity of this dielectric material, which is mica. So we're going to recall that given a dielectric material, capacitance is given us the permittivity of that dielectric, right? Times area divided by what? The distance. But we know that this permittivity of the material is equal to, well, the relative permittivity, that is dielectric constant of the material, times permittivity of free space. So we replace this permittivity of mica now, alright, with dielectric of mica times the permittivity of free space. And then multiply by area divided by what? The distance of separation. Now, I want us to look at this. You take note that this part of this equation is equal to the capacitance of the capacitor with vacuum as the dielectric, or air as the dielectric. Is that not so? So, and that's what we obtained already in the previous video. Alright, we got it as 3.7 times 10 raised to the power minus what? 10 farad. So, we can rewrite this capacitance to be equal to Kr times C naught. Where this C naught represents capacitance of the capacitor with vacuum as a dielectric. Like I stated previously, we had that C naught is equal to 3.7 times 10 raised to the power minus 10 farad. So we can just simply substitute our Kr, that is dielectric constant, is 7 times 3.7 times 10 raised to the power minus 10. And of course, let's see what this is going to give to us. We shall multiply 7 by 3.7. So it's going to give us 25.9 times 10 raised to the power minus 10 farad. Okay, we can still write it as 2.59 times 10 raised to the power minus 9 farad. You know, I move the point once to the left. So this is going to be the capacitance of the capacitor with mica as dielectric. You notice that this capacitance, alright, is greater than the capacitance when vacuum was used. That's the previous case. So what does that tell us? That once you replace maybe the space between the parallel plate, if it is filled with a given dielectric material, it increases what? The capacitance of the capacitor. Of course, we encountered that already when we discussed the factors that affect capacitance of the capacitor. It was stated that the permittivity of that material affects the capacitance. In what way? The higher the permittivity of the material of the dielectric, the higher the capacitance. Of course, we are saying that in this case, right? Now, I want to calculate for the charge in this case. For charge, alright, we're going to recall that Q is equal to CV, so that our Q is now equal to capacitance with dielectric of mica. That's going to be 2.59 times 10 raised to the power minus 9. We shall multiply by 300, which is the given potential difference. And then, if we do this, let's see what we're going to get. 2.59 times 300 times 300. That is 7,770 times 10 raised to the power minus 9 Coulomb, which is still equivalent to 7.77 times 10 raised to the power. I'm going to add the 3 times I move to the point to this. That's going to be minus 6 Coulomb, right? Good. And that becomes the result. This result can still be quoted as 7.77 micro Coulomb because 10 raised to the power minus 6 It's micro, right? So this is how we approach this problem on the board. It's a simple one. In this video, we look at a problem in which a 4 microfarad capacitor is connected in series with an unknown capacitance across a 4-volt battery source. If a charge of 8 microcoulomb flows in the circuit, it is required that we determine the value of the unknown capacitance. We should also determine the potential difference across it, that is, across that particular unknown capacitance, and then obtain the combined capacitance of the circuit. It's important for us first to have an idea of what this circuit looks like, okay? Now, we have a 4 microfarad capacitor connected with an unknown capacitance. Okay, this is the 4 microfarad capacitor. This is the unknown capacitance. Let's represent it with C subscript X. Is that okay? And then the whole circuit, okay, is connected across a 4-volt battery source. So this is a 4-volt battery source. We were told from the question that a charge of 8 microcoulomb, so Q equal to 8 microcoulomb, flows in the circuit. So this is what the circuit looks like. Now we have to determine the unknown capacitance. If you look at this problem, getting the unknown capacitance directly will be a bit complex. But we can go through a means. We can determine the total capacitance first. Of course, you know, when given a particular problem to solve, right? A calculation problem, there is no rule that you must get the first thing that you are asked to calculate. There is no rule like that. You can get the last term first as the need might arise. Maybe calculate the final thing first. This is to get the initial parameters that you are asked to determine. And of course, this question is a case like that because from what we have in the circuit, we can easily determine the total capacitance. That is the top part of the question. Why is that possible? From the question, we know the total voltage, okay, is a 4-volt battery source. We know that, and then we know the total charge in the circuit is 8 microcoulomb. So we can determine the total capacitance, that is a combined capacitance. Combined capacitance can be obtained first. Combined capacitance. So we can get that first. Can be obtained first. Which means we'll start with the third part of the question. I. Is that okay? We can say that the combined capacitance is equal to charge divided by what? The potential difference, the PD across it. And so that's going to give us, the charge from the question is 8 microcoulomb, which is 8 times 10 raised to the minus 6, divided by the voltage, which is 4. If we do that, you would notice that the capacitance, that is the combined capacitance for this circuit, is 2 times 10 raised to the power 6 farad, which is still the same as 2 microfarad. Is that clear? So we've obtained the first part of the question, which happens to be the last one we're asked to find. With this combined capacitance, we can now get the value of the unknown capacitance because we know the value of the capacitance of this capacitor. So that will now take us to the first part of the question. Now I want to know that these capacitors are arranged in what? Series. Because they are arranged in series, we have the formula which we already derived. For series capacitors, capacitor arrangement, okay? So capacitor arrangement, we already derived in our past videos that 1 over the combined capacitance is equal to 1 over, let's say, capacitance of the 4 microfarad plus 1 over capacitance of the unknown capacitor. Now, if we substitute the values we have here, this is 1 over 2, 1 over the combined capacitance, which we calculated already, equal to 1 over 4, the capacitance of the 4 microfarad plus 1 over Cx, which implies that 1 over the unknown capacitance will be equal to, we're going to move 1 over 4 to meet 1 over 2. If you do that, it's going to be 1 over 2 minus 1 over what? 4. So 1 over C subscript X will now give us, the LCM of these is 4, so if you work around that, you are going to get 1 in the numerator, okay, here. Therefore, notice that our Cx is equal to what? 4 microfarad. So we have obtained the value of what? these unknown capacitance. Then from here you can inverse to get that the unknown capacitance is equal to 4 microfarad. Right? They happen to be equal. You expect that anyway, theoretically. Okay, now let us look at the second part of the question now. The now calculate that. We are asked to find the potential difference across it. That is across the unknown capacitance. We have to calculate what? The potential difference. We know that potential difference, so I'm going to write it with respect to this unknown capacitance, alright, is equal to charge through that capacitor divided by the capacitance of that capacitor there. And so we can substitute. But before substituting, I will recall for series capacitors, the same charge flows through. So that is one thing you should know about series capacitors, but if they are in parallel, it's different charge. Okay? Now, if that is the case, it implies that our Qx will be equal to Q of the 4 microcoulomb, and that will be equal to the total charge given from the question. Hence, our Vx is equal to total charge, which is 8. So let me write that here. That is 8 microcoulomb. That will be equal to 8. I'm not going to convert this microcoulomb to coulomb. That is multiplied by 10 raised to the minus 6. No need. The reason for that is I'm going to use the microfarad value of the capacitance that we calculated, which is 4. So I'm going to substitute 8 over 4. It implies that the potential difference across this unknown capacitance is equal to 2. That is 2 volts. And this is the solution to that problem.